Hi, good morning. I'll talk about the advection of a finitely small-sized inertial particle moving in a viscous fluid under the influence of something called a memory or a history force. And this is done under the guidance of Professor Amma Govindarajan and Vishal Vasan. So just briefly describe the problem here. So consider you have an incompressible fluid with a density rho f and a kinematic viscosity nu, and it has a flow field given by u, which could be both spatially and temporally varying. And then you put in an infinitesimally small particle in it of density rho p. It's going to follow, the trajectory is going to follow the streamlines of the flow. But when you increase the size of this particle to something finite, however small, given by a, one of two things happen here. One is it's going to affect how the surrounding, it's going to affect the fluid field u. It will perturb it slightly. But this theory built under the assumption that the perturbation field is very small, which translates into saying that the Reynolds number for the particle, which is defined with this particle length scale a, and the perturbation velocity is still kept to be very small. In that sense, we're still in the Stokesian regime. And the second thing that happens is because it has a finite size now, the trajectory of this particle is going to deviate from the streamline of the flow. And the dynamics of such a particle is then given by the set of Maxwell equations. The first equation here is the usual equation for the particle's position y. Second is the force balance equation, which tells how the velocity of the particle evolves under the influence of these forces. The first of which on the right-hand side is the Stokes drag, which is kind of better known in the Stokesian limit. And then the one in the middle, which has this non-trivial form, is called the Bassett-Boussinesq history force. Both these forces are linear in nature, and then you can have other forcing, which could also be non-linear, and some other body forces, and so on and so forth. And so there are two non-dimensional numbers that feature in this equation, alpha and gamma, both of which can be described further by two more fundamental quantities, one of which is capital R, which is a function of the ratio of particles density to that of the fluid. So the larger the R, heavier the particle is compared to the fluid. Then you have one more parameter, which is the ratio of time scales. So a square by nu is the relaxation time of the particle to the fluid, or the viscous time scale. And tau is some time scale over which the surrounding changes. And this, so alpha and gamma both feature this ratio of time scales. And you can notice that they're off only by half an order of magnitude in this ratio of time scales. So if you're operating in if you're looking at a system at certain tau where this ratio is order 1, these are not off by a huge margin. So you cannot suppress the effect of history force in favor of, say, Stokes drag force or something. So you will have to take everything into account. So the rest of the talk is basically going to be how do we numerically evolve such a particle which has this non-trivial history force. So before we get into that, let's understand certain elements about this history force and what makes it numerically challenging. There are two parts to it. First one is you have this first term, which is like the initial relative velocity of the particle to the background fluid multiplied by 1 over square root of t, which clearly is singular at t equal to 0. And the second important property is this following integral, which is a time-weighted average of the particle slip acceleration, and the weight is given by this Bassett kernel, which is both time-dependent and is slowly decaying because it's only going as 1 over square root of t minus tau. And again, important thing is the averaging is happening over the entire lifetime of the particle, which renders this a non-local thing in time. So this manifests as two challenges in the numerical problems. One is that now you have to, the more you evolve into the future, you have to perform this integral over longer durations of time. That's one. That's more work, and that's growing work. And the other thing is you also have to remember the slip acceleration or slip velocity of the particle so that you can perform this quadrature as you evolve. You cannot, there's a time dependence sitting here, so you cannot just simply split this integral and write as something you know and something you have to figure out. So these are the 2 points that will mitigate using the numerical scheme that we have. Before we get into that, let's understand what are the basic tenets of an iterative numerics. And the basic idea is that you're able to prescribe an identical evolution rule that can take you from an arbitrary current state to a future state. And the emphasis I want to make here is on the word identical and an arbitrary current state. And to explain those two factors, let's take a model semilinear ODE. And we know how, there's enough, we all sort of solve this using traditional methods. So let's see what goes into it and what makes it an identical evolution rule. So let's consider an evolving variable x, which evolves according to this equation, which has a linear part c times x and a nonlinear term. You hit it with e power minus ch, where h is like the size of the time step you want to take. and you integrate it over a certain time t to t plus h, and you end up with this integral equation. And this is a testimony to how an identical evolution rule should operate, which is you can take any current state, an arbitrary state, hit it with a propagator which is time independent, and that takes you to the new state. And it also advects a nonlinearity over the new bit of history, which is only from t to t plus h. So one key point is that you have this propagator which is time independent. A couple of more things you can observe in this. If you put the c equal to 0 limit, it becomes a totally non-linear problem, and then we can sort of use any standard time integrated method such as Runge-Kutta and so on. And when you put non-linearity to 0, this integral form that we have, this is an exact solution. It's solving the linear part of the equation exactly. So this sort of guides us towards what we should be looking for, if at all, if we're looking for a propagator. And let's look at how our system is different from this model equation. Everything is same except that we have a history force here, which is sort of changing the linear operator here. C of x is the Stokes drag we had in the Maxi-Reilly equation. Non-linearity is other forces. So we have to figure out, in the presence of this history force, can we also write a statement like this and find a time-independent propagator, which also and the way we can do it is that it also solves a linear problem exactly. And we try to look for such a thing exactly. The corresponding linear problem in the Maxi-Reilly equation will be to solve for this operator, the homogeneous part, and for a particular initial condition. And if we get to do that, probably then we can also build a similar numerical technique. And in order to solve this operator, we sort of take help from the results from 1D heat equation. So in the 1D heat equation problem, so let's consider you have a diffusing variable W, which is defined over a fictitious domain Z and time t. It's a known result that there is a correspondence between the Dirichlet condition and the Neumann condition for such a problem. This mapping is basically, can be explained basically using this example. So consider you have a semi-infinite rod and you are sort of tracking the diffusing temperature variable. At the infinite end, things are decaying to 0, but the fixed end, you are allowed to either prescribe the temperature, which can be time varying, or you can prescribe the flux condition, and each of which would induce a temperature profile across the semi-infinite rod. The question we ask is, what is the pair of equivalent temperature and flux condition that you can prescribe that will induce the same temperature profile across the length of the rod? And that's exactly the statement of this Dirichlet-Neumann map. So it says, if you have a Dirichlet condition W at the Z equal to 0 boundary, the equivalent flux condition should relate to this Dirichlet condition in exactly this form, so that you get the same temperature profile or the diffusion profile across the domain. And you can notice that the expression on the right-hand side is very reminiscent of the Bassett history force, except for a minus sign. Now, can we make use of this idea in building the numerics? So this goes back to the idea that was explored by Ganga Prasad in 2019, which is they established the exact mapped system where we can make use of this heat equation property. So we have here in the original system where the particle is moving from an initial, at a time t0 to t1, and its trajectory is evolving according to the Maxi-Reilly equation that we had seen before. Correspondingly, we can build a map system for the 1D heat equation where the diffusing variable is W, initial condition in the bulk is set to 0. And we make a mapping that this diffusing variable W on the boundary Z equal to 0 is mapped to this relative velocity that appears in the Maxi-Reilly equation. Now, once we do the mapping on the boundary, the same diffusing variable has to also evolve according to the Maxi-Reilly equation, except that because we have extended this problem, now we are able to replace this non-trivial, non-local time function with a Neumann operator because of the Dirichlet-Neumann operator that we had in the heat equation. And now this becomes an unsteady Robin boundary condition. Now this heat equation system with this unsteady Robin boundary condition can be solved, and it was solved by Ganga in his paper using unified transform method. And once we do that, we can end up with a similar equation, an evolution rule, which can take from an arbitrary state Q of t to a future state Q of t plus h. And we have in the process also identified our linear propagator, which is chi, which takes this following form, quite different from the exponential. But it's still not an identical rule because this, I've written h here, it's abstracting the exact form, but it is reminiscent of the fact that we are carrying a bit of memory from the past. So that still occurs here. We still have to figure out how to compute this or do whatever that is, how to evolve this and sort of close it and make it an identical rule.
Divya, this is your 10-minute warning.
Sure. Thanks. Let us look at a few properties of this chi, and we'll compare it with the exponential. And why we do that with the exponential is because if we put the gamma to 0 here, this function exactly reduces to e power minus alpha t, which is the case when corresponding to Max-Rayleigh equation without the history force. So comparing this with the exponential will help in understanding what you would miss out on if you were negligent about missing out on the basic history just because you didn't know how to deal with it. So the initial time behavior at t equal to 0, both exponential and chi is 1, which is good. But the derivative is, it blows up for chi, but it's well behaved for exponential. Asymptotically, exponential decays as exponential, but this has this decays algebraically with x power minus 3/2. And the third property, which is more relevant to building a numerical technique, is the semigroup property, which takes in additive groups to this multiplicative. And it can be shown that because this chi function here does not obey this rule, that leads to this additional that features in this rule, the evolution rule. So I'll just explicitly tell how that function, the thing that I abstracted in the previous slide, it takes the following form, which is an integral over this variable k, and the integral is running over the entire real line. So how do we close this system? That the thing is that in the heat equation map system, we also can derive an evolution equation for this curly h, which features here in the last equation, which if you notice evolves according to the exponential propagator now, and this can be solved as usual. Now these three set of equations completes the whole thing. Given that you know how h also evolves, you know how this evolves. So this everything becomes like closed, and you have an identical rule. So what we've done is we have inflated the size of the system to include these different modes of curly h, but this is only a fixed number of curly h's, as opposed to in the original system where we would have had like q and yz at all the times from present to the past, an entire thing in the history. Now we are replacing it with a finite size object, like there could be k number of modes, and we have to keep track of those at every time instance. And that leads to, now it becomes conducive for an iterative numerics, and the way we this helps in the numerics is that we argued that in the brute force approach, you will have an increasing computational cost and as well as the memory storage cost. In this, both of that will reduce to a fixed fixed computational cost, because once you fix the number of k modes you want to use to approximate this integral, that's a fixed number, and you can do that in every time step. And then because you've redefined the system to include only k modes of this new h variable, that's also fixed memory cost. So once you've given these details, you can always advect to a new state. You don't have to remember everything in the past. Okay, I'll skip that. I'll now tell how the computational performance fares with this method, and I'll use this model equation where the forcing is like a simple oscillating dependence on time. On the left-hand side, so I'm evolving the system to certain time, which is on the x-axis, and I'm plotting the computational time it takes. So the blue line is for the brute force, where we actually compute this integral over growing lengths of time. At every n step, you have to perform a quadrature of n points. So it's going to scale as n square. So that translates to a proportional computational time. So you see the quadratic growth. On the other hand, in our method, at each time step, at nth time step, you only have to perform like m operations, which is a fixed number. So you see the linear growth here, and the slope is going to be the amount of work you do at every time step. Correspondingly, I mean, this is basically to show that we can achieve different accuracies. And if you design a first order method, you get that error convergence rate. And if you design h square, you can go on with a higher order schemes as well.
Divya, you only have a minute left.
Sure, yeah. So these are some numerical experiments we had done with our numerical scheme, just to highlight how the history force behaves. So the first one is when the forcing is basically the sign of lambda t that you prescribe. And here the black is without the history and the blue is with the history. You can see, I mean, it's not very evident here, but there's a slight phase difference between the responses of these two when you have history versus when you do not have history. The second is, again, if you gave a Gaussian impulse in time, how does it behave? You can see that with the history, initially it decays rapidly, but which is because you have a 1 minus gamma times square root t behavior initially. And at long times, it stretches, it's fatter than the exponential. So it decays slowly. That's highlighted in this experiment. And this is a nonlinear case that we have taken, where the nonlinearity form is this. And I've just shown it for different initial condition. And this is the black dotted line is the corresponding stable fixed point when we didn't have history. So these are all approaching that fixed point at different distances, which is proportional to the gamma, the amount of history that you have had to include in your problem. Yeah, so with that, I'll just be concluding that we have now an explicit time integrated method, which incurs only a fixed computational cost and a memory cost. And now with this difficulty out of the way, we can perhaps do longer runs in, say, in flows like turbulent flows and see what particles with memory, how do they cluster in a fluid, and so on and so forth. Yeah, that's it. Thank you.
Thanks a lot, Divya. We'll entertain a couple of questions.
Hello. So 2 questions. One, like how many values of K did you take?
Values of?
K.
K again depends on alpha and gamma. So you have alpha and gamma will dictate how many Ks you should take, but even in brute force approach, you can do sort of the convergence that you get. That can be one dictating factor. And alphas and gammas can dictate how you.
But for the, let's say for the plots that you had, like what is the typical?
So I had to take like 50 points to perform the quadrature for this one.
Okay. Another somewhat more vague question. So this kind of this extra dimension that you're looking at. So is there a physical way of saying what is that variable in the fluid particle problem that you are thinking about? Is it telling us something about what is happening in the particle fluid system?
I mean, in some sense, storing where it had been in the past, right? I mean, if we didn't do this heat equation mapping and stuff, that the state description would be that you need Y at all the previous times and the Qs in the past times. So that's basically remember everything. That would be the state description. In this mapping, we're just able to reduce that to a fewer points because we are now talking about a local term in space in this map system.
But I was thinking whether it is some record of the stress that is there in the fluid, which is then affecting that.
Yeah, so the history force is an inertial and a viscous stress. So it's keeping a record of all of those things. Yeah, that's one. Yeah.
Okay, thank you.
Handle the history term. Can't you work in the Laplace space and get rid of that because it has this convolution structure?
Which one?
You had an equation for Q. Here, I mean, yeah, after this, no, before this. Yeah, here for Q, the history term has this convolution structure. So can't you work in terms of Laplace variables and get rid of that?
I haven't tried that, but I still, but you still have to be computing at every time, right? It's a different value. Yeah.
But you won't have integrals then.
Oh, you're saying you work in the Laplace space, is that what you're saying? Yeah. I don't know how exactly it will not help this problem, but yeah.
So I mean, this memory term that you have, I'm here.
Sorry.
Yes, no, this memory term that you're writing. So I mean, how does it actually come? Like when you are deriving, normally we have the Stokes force. I mean, that's if you saw from Navier-Stokes, you can get it. So I mean, how does this come? And like supposing I'm just dropping a ball in a viscous fluid. I mean, is that term important? And like one should really keep it? I mean.
Okay. So the first answer to the first question is, so when you in the entire Navier-Stokes equation, when you just neglect the u dot grad u, the non-linear term, and the unsteady equation so if you compute the stress because of the unsteady equation for the perturbation velocity, you will end up with that equation. So that's one. And second is when you're dropping the ball in this thing, I think in the initial time, you should be caring about the history force. Maybe long time dynamics, you don't have to, but initially it will do a lot of different things from when you're neglecting it. And also depends on the system, like the particle size and all the other properties which you're looking at.
But you don't know if it has been observed experimentally, like it has.
Yeah, I haven't seen it. Yeah.
Thanks.
Okay, thank you, Divya.